Part two of the Introduction to Amateur Astronomy lecture series is entitled Discovering the Night Sky. So it's with part two today that your journey toward becoming an amateur astronomer really begins. Last time we got all the scientific stuff taken care of. This time we're ready to get into kind of the really heart of being an amateur astronomer, which course is the night sky. So your very first step as an amateur astronomer is not to buy a telescope. I mean, it's the worst thing you can do getting started as an amateur astronomer. But like many of us, like me, for example, you may go out and buy a telescope or have one purchased for you as a Christmas present. And at first, you'll have a lot of fun. You'll look at stuff like the moon and its vast array of craters and mountain ranges and vast volcanic plains. You'll have a blast looking at Jupiter. You'll look at the belts and zones, the great red spot, and the 4 Galilean moons dance around the planet. And of course, you'll be mesmerized and blown away by the planet Saturn. Many people think when they see Saturn for the first time that it's like a slide in front of the telescope, because they can't believe what they're seeing is real. So you'll have a lot of fun doing that if you've never seen Saturn before. And if you're lucky, you might even stumble across some deep sky objects. The Orion Nebula, shown here, is really easy to find. And maybe you'll point at a few random stars in the sky, and you'll be lucky enough to come across a double star, maybe a true binary star system. But then you're going to ask yourself, what else is there to look at? Because if you jumped right to the telescope, you skipped all the important intermediate stuff. You need to learn how to, navigate the night sky. You got to be able to identify the bright stars and constellations, and then work your way up to binoculars, and then finally a telescope. So that's why the Introduction to Amateur Astronomy lecture series is, organized the way that it is. We don't start with telescopes. That's not until part 4. So what happens when you get your fill of looking at the moon and the brighter planets and maybe some deep sky objects, you'll get frustrated and you'll stick your telescope in the closet, and you'll probably end up selling it in some yard sale for, $5, or you'll try to sell it on Craigslist, because I've seen plenty of junk telescopes on there. So definitely do not begin with a telescope, because not only do you not know the night sky very well when you get started, but odds are you'll pick the wrong telescope and you'll just get frustrated with it, and it'll just collect dust and cobwebs and stuff like that. So your very first step as an amateur astronomer is to educate yourself. And as I mentioned in the companion notes, there are lots of great websites out there. I highly recommend the ones from, magazines like Astronomy, Sky and Telescope, The Sky at Night, and stuff like that. So they always have great beginner articles that they post on their website. And there are many other websites that have, really excellent information. Some not so much. The internet is still very much the Wild West. So some of the information you might find is not really great for the beginner. But still, it's maybe old-fashioned by today's standards, but the absolute best information for the amateur astronomer is still in good old-fashioned books. And these are 3 of the best. I do own a copy of The Practical Astronomer. I purchased that during a previous version of this series, but I still haven't really had time to look it over. But the ones I recommend above all others are Night Watch and The Backyard Astronomer's Guide. Both are either authored or co-authored by Terence Dickinson, but as you may know, we lost Terence in February of 2023, so rest in peace, Terence. He was a great guy. And but now the latest edition of Night Watch has been kind of updated by Ken Hewitt-White, with some stuff added in by Alan Dyer as well. And of course, Alan Dyer is the longtime co-author of The Backyard Astronomer's Guide. And I do want to mention, if you do not have copies of these books, we do have them available for purchase in our online store called the Sky Shop. Yes, I freely admit you could probably get them cheaper at like Amazon, but doesn't Jeff Bezos have enough money? So if you want to help a nice small astronomy club like us, and you really need copies of these, you're welcome to purchase them from us on the Kalamazoo Astronomical Society website. So Night Watch is really kind of the textbook for this lecture series. But if you really have an interest developing an astrophotography, then probably you would like the Backyard Astronomer's Guide. But they did add some stuff to Night Watch recently too, the newest edition of Night Watch, which came out just late last year. And the current version of the Backyard Astronomer's Guide came out in 2021. So they're both relatively up to date. And again, I can't recommend them enough. I mentioned that I used to sell telescopes. And one day in the telescope shop, I was very bored. I figured, hey, why don't I write a book? So I started working on an outline. And then one day I got Night Watch in. And guess what? My outline and Night Watch were almost exactly the same. So there went my book. I figured, didn't need it. We already have Night Watch, but they are both excellent guides. I can't recommend them enough. But if they are a little too expensive for you, the Practical Astronomer is a lot less expensive. So if you really need to save money, I believe the Practical Astronomer is around $20, $25 or so. So we all know that Earth rotates on its axis in a 24-hour period that we call a day. So yes, the Earth does rotate at a speed of 460 meters per second, or 1,000 miles per hour, at least at the equator. But this rotation of the Earth on its axis, of course, affects the way we see the sky during the course of a day. So as the Earth spins on, we see the sun, the moon, the planets and stars appear to rise in the east and set in the west. It was Nicholas Copernicus that finally published the first serious work on a heliocentric or sun-centered solar system in the year 1543. He wasn't the first to come up with the idea, but he was the one to really popularize the idea. And yeah, it's been nearly 500 years, and we still say sunrise and sunset as if the sun actually moves. But it makes the language a lot easier. So here we see the sun setting over Lake Michigan on a very nice day. So as the sun slips below the horizon, the first thing you'll probably see is the moon, because if the moon's already above the horizon, it's probably easy to see even before the sun sets. But maybe it's a skinny crescent and you really can't see it until the sun's low. So the moon will be the first thing you see. And then the planets, if they're out, like Venus and Jupiter. But gradually, as the sun does set further and further behind the horizon, the sky will grow darker and the stars will begin to appear. Bright stars first, and then fainter and fainter stars as the sky grows darker and darker. And before too long, the sky is full of stars. So if you are at a dark site on a very clear night with no moon, no city nearby, you can see approximately 3,000 stars on a given night. Now, of course, in this time lapse image, in this time exposure image, there are a lot more than 3,000 stars just in this picture alone. But with your eyes alone, the average person can see about 3,000 stars. And one thing we humans like to do, or we're kind of trained to do, is look for patterns. People see, funny shapes in clouds, like puppy dogs or stuff like that. Some people see religious figures on burnt in their toast. But of course, the original version of this, the original version of connecting the dots, is creating patterns in the sky that we call constellations. So the constellations originated in Mesopotamia over 5,000 years ago. And it's all centered around modern day Iraq, right around Baghdad, Iraq. So we can trace back the history of the constellations roughly 5,000 years or so. And of course, other constellations, largely based on the Mesopotamians, were added by the Babylonians, the Egyptians, and the Greeks during the classical age. And starting with the voyages of discovery, 1492, Columbus sailed the ocean blue, people started going further and further south of the equator, where they saw all new stars for the first time. Of course, humans have seen these stars far south of the equator for many, many centuries before, but we have that European bias going here. So when Europeans, started sailing further and further south of the equator, they saw all new stars that they've never seen before. So they made up newer constellations. And you'll notice there's a big difference between the classical constellations and the more modern constellations. So the classical ones, they're named after figures from mythology. But the more modern ones were named after great inventions of the day, like there's sextants, the sextant, there's telescopium, the telescope, microscopium, the microscope, and so on and so forth. So if we were to reinvent the constellations today, we might have the constellation of the airplane or the automobile or maybe the laptop computer. You could say the smartphone too, but man, that would be a pretty boring constellation. So every culture had basically their own set of constellations. So way back in 1928, the International Astronomical Union established 88 official constellations at one of their annual meetings. I think it was like in the Czech Republic or something like that. I forget exactly where they held the meeting at, but that's not really important. So yes, they kind of established 88 official constellations with boundaries. So of course we have borders on the surface of the Earth. Now we have borders in the sky, and they're both, of course, quite imaginary. So here's an example of that. Here we see two prominent constellations of fall. We have Pegasus, the winged horse, and we have Andromeda, the princess. And you'll see they have their borders. Now, to the International Astronomical Union, any star inside the border of Pegasus here belongs to Pegasus, even like this one, or say this one down here, or this group of stars down here, even though, they don't necessarily make up the stick figure of Pegasus. Just like any city within the borders of Michigan belongs to Michigan. So any star within the border of Pegasus belongs to the constellation Pegasus. Again, even though it's not part of the pattern. And you'll notice the lines are still connected to Alpheratz here, which is just across the border in Andromeda. Now, the lines, and I'll mention this again later, are not universal. The International Astronomical Union did not establish 88 different ways to draw, or one way to draw the 88 official constellations. So you'll see lots of star charts label or draw the constellations differently. So there's no rule that says we amateur astronomers can still connect these lines to Alpheratz, even though it belongs to a different constellation. So yes, over here we have Andromeda. And you'll notice we have the square that I have labeled the Great Square. And this is basically a different type of pattern called an asterism. So asterisms are unofficial groups of stars made up of parts of one constellation or bright stars from several constellations. So the Great Square is an example of an asterism of bright stars from two different constellations, 3 of them from Pegasus, 1 from Andromeda. But by far, the most popular star pattern in the entire sky is the Big Dipper. There are 3 stars in the handle, 4 stars in the bowl. And of course, they all have their own unique names. And I've been doing this for nearly 45 years now. And if you probably quiz me on the names of the stars of the Big Dipper, I still might even get a few of them wrong. But I think I know them pretty well now. So yeah, we have Alkaid, Mizar. Alcor is nearby. This is an optical double, not a true binary star system, but they are both binaries. We have Alioth, Megrez, the faintest star in the bowl, Thad, Merak, and Dubhe. But even though the Big Dipper is very famous and pretty much everyone can identify it if they see it in the sky, it is not a constellation. It is, in fact, an asterism. In fact, we really only call it the Big Dipper in the US and Canada. Usually, in England, they refer to it as the plow, but maybe there's been that American influence and they call it the Big Dipper as well. So the 7 stars of the Big Dipper are in this case part of a much larger grouping of one constellation called Ursa Major. And Ursa Major, of course, is the Great Bear. There are 3 stars that make up the tail. So yep, this bear has a long tail. More on that later. The top of the bowl of the Dipper is the bear's back. This is the bear's nose, maybe an eye here. There's a front leg here with 2 stars marking her paw. Yes, it is a female bear. There's one back leg here, 2 more stars marking her paw, and 2 more stars here marking another paw. So yeah, one paw is kind of missing in action. So, of course, with a little imagination, you can easily picture a bear, but here we go, thanks to technology. And it looks like a very nice bear, but it does look a little odd with that long tail, but more on that in a minute. So you'll notice that many of the stars have, names, proper names. Another example is Sirius, which is the brightest star in the night sky. But just from the name Sirius, you would never know that it was bright. And it doesn't even tell you what constellation it's in. So everyone loves to learn the name of the stars. You can impress, your date on a nice clear night, take them out to a empty field, and you can impress them with your knowledge of star names. But, it's not a terribly useful system. Very colorful, but not very useful. So a much more useful way to designate stars is the Bayer designation. So in this system, you have a Greek letter, alpha, beta, gamma, delta, all the way to omega, which is usually in order by brightness, but not always. There are some exceptions out there, like in Orion, the alpha star is not the brightest. And it's followed by the genitive or possessive form the constellation, is found in. So here we have another example, Alpha Canis Majoris. So right away, with this designation, the alpha tells us it's most likely the brightest star in the constellation. And if it's one of those exceptions, it's maybe not the brightest, but it's pretty close to being the brightest. But in this case, it is. It is the brightest. And it tells you it's in the constellation Canis Major. And yes, Alpha Canis Majoris is the exact same star as Sirius. And you'll find that stars have many different designations. Of course, most of those are numbers. There's the Smithsonian Astrophysical Observatory, which has SAO first, and then I think 5 or 6 digits. There's the Hipparchus catalog. One you'll see a lot is the Henry Draper catalog, especially if you like extrasolar planets. Whenever they announce the discovery, they usually give it by its HD number. And there's, of course, the Tycho catalog as well. And there are others like the Hubble Guide Star catalog. But more modern catalogs, like I believe the Tycho catalog, instead of just kind of these random numbers like Henry Draper catalog or the SAO catalog, the number is their right ascension and declination. Basically their latitude and longitude, but in the sky. But of course, for we amateur astronomers, we mainly go by the proper names when we can, but oftentimes we have to go by the Bayer designation because, it's hard to name every star in the sky. And I'm assuming many of you have spent some time under the stars already, and you'll notice the stars have different brightnesses. So astronomers today measure the brightness of stars using what's known as the magnitude scale. And this system has been around for a very long time. This system first appeared in the writings of Claudius Ptolemy in about the year 140 CE. But it's very likely the system may have originated earlier than Ptolemy because Ptolemy himself makes references to Hipparchus. So most astronomers attribute the magnitude scale to the Greek astronomer Hipparchus. But Hipparchus, having lived roughly 2,000 years ago, is not terribly well known, unfortunately. So much of his work has been lost. Now, the way it worked for them, thousands of years ago, is really the magnitude scale grouped stars by size, or bigness. They assumed, that the stars that to us were brighter were actually larger. Maybe they were bigger holes in the tapestry of the heavens, so they let more light through. But of course, today we group the stars by brightness, not by size, because there's no correlation between the two, at least in terms of the magnitude scale that we're talking about. So the way it worked originally, and still works today, is stars were put in the classes ranging from 1 to 6, where a first magnitude star is the brightest and a sixth magnitude star is the faintest. Now, this only includes stars that you could see with the unaided eye. But of course, today, modern astronomers can measure the brightnesses of stars to high precision using devices like, digital cameras, CCDs or CMOS cameras or photometers. So today we can do this to great precision. And we measure the magnitude of everything in the sky, not just the stars, but the planets, even the sun and the moon, even satellites that can pass overhead. So here's some examples of these. So obviously the sun is by far the brightest object in the sky. It's way brighter than any star we see in the nighttime sky. So notice that we had to go way off into the negative magnitude scale. And at first, the magnitude system seems really backwards, because you might want to say the larger the number, the brighter the star, but it's the exact opposite. The larger the number, the fainter it is. And the smaller the number, going off into the negative scale, the brighter it is. So once you get used to it, it really seems to make perfect sense. So maybe that's why it's never been changed. It just seems like a great system to have. So yep, the sun, it's at a pretty constant magnitude. It never does fluctuate. It's always around minus 28 magnitude. But I've seen it listed online as minus 27 too. The full moon at its absolute brightest and most obnoxious, sorry, I'm an amateur astronomer, I don't like the moon, it maxes out at about minus 13. Venus at maximum brilliancy is about minus 4.5. The brightest star in the night sky, which we learned is Sirius, is about minus 1.46. This little star here is Polaris. Now, many people expect Polaris to be the brightest star in the sky, but actually ranks only 48th in brightness. So it's about magnitude 2, which is well within the visual range, because this little guy here, he represents how faint we can see stars with just our eyes alone. So the average person can see about stars to 6 magnitude, but there are people out there with exceptional eyesight. Maybe they eat a lot of carrots or something, I don't know. And they're under very dark skies, and they can see to about 7.5 magnitude. And way over here, the faintest stars, or really galaxies, the Hubble Space Telescope has ever imaged are at about 35th magnitude. You might wonder, why don't I put the James Webb Space Telescope there? Well, it's mainly an infrared telescope, but in visible light, Hubble hasn't gone further than 35th magnitude. So these numbers are known as apparent visual magnitude, and it's also denoted as a lowercase m with a subset v. And this basically describes how stars look to our earthbound eyes. Maybe the star is bright just because it's nearby. Sirius is really bright, because it's only 8.6 light years away. But if we were to replace the sun with Sirius, it would still be brighter than the sun in the sky. So Sirius really is brighter than the sun, but of course it's fainter because it's 8.6 light years away. But maybe stars are only bright because they're nearby. Maybe they're faint just because they're small or far away. So there's another scale called the absolute visual magnitude. And this is the apparent magnitude stars would have if they were all 10 parsecs away, about 33 light years, 32.6 if you want to get technical. But for amateur astronomers, we don't really worry about the absolute visual magnitude, but it is important if you want to know how much energy a star emits besides, visible light. So with the apparent magnitude scale, it's defined so that two stars that differ by 5 magnitudes have an intensity ratio of exactly 100. Now, I won't bother to get into the intensity ratio today, but there is more information about that in the companion notes to the series. But again, for we amateur astronomers, it's not terribly important. So basically, two stars that differ by 1 magnitude have an intensity ratio to the 5th root of 100. So of course, in math, here's the 5th root of 100, but if you don't like that, you can take 100 to the 1/5 power, because it's the same thing, and we get 2.512. So a first magnitude star is 2.512 times brighter than a second magnitude star. So that puts it in some perspective for you. But it's not really terribly important. But here today we have the heart of the lecture, and this is how to read a star map. So the star map I will use is the one I developed for the Kalamazoo Astronomical Society. There are many other star charts out there. I mentioned, magazines like Astronomy and Sky and Telescope. If you open to the very center of the magazine, they have their own version of an all-sky star map. That's very nice. You can purchase a subscription from Abrams Planetarium, and they'll send you a nice star map along with their sky calendar. You can download the one from skymaps.com, which is very nice, but I'm biased and I like mine the best because I made it, and each one took about 6 hours to make. So the first thing we should check out is in the upper right-hand corner of the chart here. And so it says this map represents the sky at the following local standard times. And you'll notice, for say late February, this is how the sky looks at 8 p.m. But you might be asking, hey, I like to get up before dawn, before I go to work maybe, and do a little stargazing if it's clear. So if you're up at like 5 in the morning, to do a little stargazing, this star chart won't be very good. Because of course it's set for the early evening when most people are up. So what you want to get, and really everybody should own one, is a planisphere. I've been an amateur astronomer for over 45 years, and I have an amateur astronomer in my chart bag, which I don't use very much these days because I mainly take pictures, but that's besides the point. So a planisphere is like the abacus of star charts. It doesn't require batteries, but by turning the wheel, you can set it for any day or time of the year. Maybe the only drawback of the planisphere is it can't show you where the planets are because, of course, the planets move in a very different fashion because they orbit the sun. So the one that I like the best is the Miller planisphere. And this also happens to be the one that we sell in our online store as well. So besides those cool books, you can purchase a Miller planisphere from the Kalamazoo Astronomical Society. All the ones that are shown here are very nice though, and they're all plastic because, in Michigan in the summer, it gets very dewy at night. So if you have kind of one of those heavy paper planispheres, that won't last very long on a nice dewy night here in Michigan. And the Miller planisphere comes with a nice plastic case you can keep it in too, so it doesn't get all scratched up. Okay, now I know what you're thinking, but Richard, I have one of these apps on my phone and I can hold it up and it can tell me what stars are in the sky. So here's my brief rant on smartphones. I hate them. I mean, I did have to buy one back in October when I traveled out west by myself to see the annular eclipse, but I don't use it. It's currently turned off and stuck in my closet. I only use it when I travel. So I'm not a smartphone fan. I can't stand them. But they're fine, but there are just some applications where the old school approach is the best. And learning the night sky is one of those because, number one, when I tried my app out on my either iPad or smartphone, I didn't find it to be terribly accurate, to be honest. And number two is you have the screen shining in your face, and that's going to ruin your night vision. More on that here shortly. So just for once, put the screen away. We look at screens all the time, smartphones, laptop, desktops, TVs. put the screen away, get yourself, a planisphere or a star map, and print it out if you have to, and go out and identify the stars the old-fashioned way. It's the best way to do it. Okay, now let's go back to our star map here, and let's identify the parts on the map. So obviously, inside this big old circle, we have a bunch of dots. And of course, the dots are the stars, duh. But the bigger the dot, the brighter the star. They're not really calibrated precisely to their magnitudes, but I tried to make the size of the dots, roughly to scale according to magnitude, but I'm sure you could find a few errors here and there. And you'll notice that many of the bright stars are in fact labeled, like Capella, which is way up there, and like Regulus, for example. So you'll find that bright stars will be our guideposts to navigate our way around the sky. And many of the stars are connected by the imaginary lines that make up the constellation patterns. And as mentioned earlier, there is no universal way to draw the constellation lines. So if you do look at different star charts, and that's totally fine, I won't be offended if you don't use my star chart here, you'll notice the way the constellations are drawn are not exactly the same. But with that being said, this is my star map. So they are drawn the way that I like to look at them in the sky. But, there's, again, no accepted way to do it. And you'll notice that constellations are labeled in uppercase, like Orion, Oregon, Leo. So that's pretty standard on every star chart and planisphere I've ever seen. And asterisms, like the Big Dipper, which we met earlier, or the Great Square of Pegasus, or just the Great Square to its friends, they're italicized. And you'll notice there are many objects that have the letter M in front of them, followed by a number like M42, the Orion Nebula. Those are deep sky objects, and we'll talk more about what the M stands for next time. And of course, we have this blue thing arcing across the map here. That, of course, is the Milky Way. Now, let's figure out how to find directions with stuff in the sky, because you can see outside the circle, we have the cardinal directions: north, south, east, and west, of course. So, if you're out at night, with your phone put away, no cheating, what do you use in the night sky to find directions? And of course, the answer is Polaris, the North Star. But out of all the stars in the sky, which one is Polaris? So to be able to find it, you have to know the trick. And without using the star chart, you have to be able to find at least the Big Dipper. Most of the time, that's really easy, except for the fall in the evening, because the Big Dipper is very low on the northern horizon. So this is almost its orientation during the fall, but it can get even lower on the horizon. From my latitude of 42 degrees, the Big Dipper never rises or sets. It's always above the horizon. So it's what we call circumpolar. So you got to be able to find at least the stars of the Big Dipper all by yourself. And then look at the two stars at the end of the bowl. And those are called the pointer stars because they point to, you guessed it, Polaris, the North Star. So draw a line as far as the Dipper is long to a star of equal brightness to the pointers, and that is none other than Polaris, the North Star. But the great thing about doing this is when you do it successfully, you have found another asterism. You have found the end of the handle of the Little Dipper. So yep, here's Polaris right there. We'll turn on the old labels there. So there we have Polaris, Cocab, and Furcad. And those are the three stars in the Little Dipper that are the easiest to see. But the other two stars in the bowl and the other two stars in the handle are pretty faint. From my usual observing site, at least with the public, these are all about fifth magnitude, and they're just barely perceptible on a good night thanks to light pollution. And yes, you'll notice this one just has a Bayer designation, Epsilon Ursa Minoris. Some sites list it as Eurodelis, but that is not its real name. Somebody made that up. So I'm sure I didn't say it right anyway, but it doesn't matter because this star really has no proper name as far as I know, at least not a very, very well-known one. So just like the Big Dipper is part of Ursa Major, the Great Bear, the Little Dipper is part of Ursa Minor, the Lesser Bear. But yes, again, this bear has a very long tail, so he looks more like like a jacked up squirrel, a squirrel that took its workout regimen very seriously, and he's all pumped up, ready to go. So yeah, these bears do look a little odd with those really long tails. So you might ask, why do these bears have long tails when they really have, short, stubby tails? Well, there's a story behind this, and it all centers around the king of the gods. Oh, and here we go, Zeus. Yep, every time I mention Zeus, he pops up with that music because if you know anything about Zeus, he thought he was pretty hot stuff, man. So he's quite notorious or really infamous in Greek mythology. So here he is looking pretty jacked up, and one day he decided to take a walk amongst the woods. He walked away from Mount Olympus, and he was walking in the forest, and he came across a very beautiful woman named Callisto. And if you know anything about Zeus, he fell in love very easily. So he fell in love with Callisto, and eventually they got married and had a young son named Arcus. Now, during this happy period, what Zeus forgot, of course, is that he was already married to Hera. Here she is. And when Hera found out about the union between her husband Zeus and Callisto and the fact that they bore a son named Arcus, she was very upset. Okay, maybe not that upset, but she was pretty upset. So what she did to punish Zeus and Callisto is she turned Callisto into a bear, a regular bear with a short, stubby tail. And, she looked like a bear and she thought like a bear. So she became a bear thanks to Hera, and she wandered off in the woods. And then many years go by. Arcus is kind of grown up, and he's hunting in the woods with this bow and arrow, and he comes across, this bear. And Zeus was keeping a watchful eye on Arcus. He lost track of Callisto, and he saw Arcus about ready to, hunt his mother, who he didn't recognize, of course, as the bear. He was a very young child when Callisto was turned into a bear. So to save Callisto and maybe protect Arcus, he changed Arcus into a bear as well. But now that Hera kind of knew where both Callisto and Arcus were, Zeus had to protect them further. So he decided to place them in the heavens where Hera could not touch them. But this is a tricky ordeal because you can't grab a bear by the ears or say the snout, you'll get bit. You can't grab them by the claws because look at that. Look at those sharp claws there. So the safest place to grab the bear was by its short, stubby tail. And as he threw the bears around and around and around, he threw them up into the sky. But because they were so heavy, he stretched out their tails. And that's why the bears have long tails in the sky. That's that's the long version. You want to hear the short version? The short version is space bears have tails. There you go. All righty. So now we know how to find directions. And you can see I have it on the chart here as well. We use the pointers, go to Polaris, and go straight down to the horizon. And that's due north. And the great thing about directions is when you find one, the others are a snap. So if you have a star map like this in front of you, hold it so north faces north. So you'll see that north and south line up correctly, but east and west are backwards. Now, why is that? We don't put east and west on opposite ends of a road map because, of course, the road is on the ground, but the stars are overhead. So if we didn't reverse east and west, the star patterns would be mirror imaged. But the best way to do this is to hold the chart up over your head. So again, north faces north. And when you do hold the chart over your head, so north faces north, you'll see that north, south, east, and west all line up correctly. So perfect. Now, of course, you don't want to hold the chart up over your head for, maybe an hour or two under the stars. So here's the best way to hold a star map is, let's say you're facing west. So rotate the map so west is at the bottom. And when you do this, the constellations should be in roughly the same orientation as you see them in the sky. And of course, with a static star map like this, you have to be out when the star map is set. If you're out at 5 o'clock in the morning, then you got to set a planisphere at 5 o'clock in the morning, accounting for daylight time, by the way, because planispheres don't account for daylight saving time. And, hold it so west is at the bottom and things will line up correctly. All right, so that's how we find our directions. Now, there are two other important reference markers. The next is the circle itself. Now, the circle is the horizon where the sky meets the ground. So all along the edge of the chart here is the lowest part of the sky. And of course, everything rises in the east over here and it sets in the west. So Leo is rising and the great square of Pegasus is setting. So if you're, for late February, for example, this is set for 8 p.m., remember, but let's say you're out at 10 p.m. Then by then, Leo will probably be over here somewhere. So everything's going to kind of rise and arc across the sky because everything appears to revolve counterclockwise around the North Star. So if the circle is the lowest part of the sky, where's the highest part of the sky on the map? And of course, the answer is the zenith. And right now, the way the chart is set, Capella is like right at the zenith. But eventually it'll move onward here and set in the west. But right now, at the time the chart is set, Capella is like right at the zenith, but it's not always going to be there because this, the Earth is, it keeps on a turning. All right, so here's how you find any star or constellation in the sky with the use of a simple star map. And it's really easy. I mean, it's faster to do this outside than it is for me to describe it to you here today. So let's do an easy one here. In the notes, I do Cancer, but since I've done that one in the notes, let me do Leo. All right, so find Leo on your chart. And as mentioned, it's kind of rising in the east. It's still very low above the horizon. That's kind of a clue for later. So put your finger, either physical or mental, at the zenith, the very highest part of the sky. And remember, no matter where you are around the world, the zenith is always the point directly over your head. Now, I'm going to draw a line from the zenith through Leo. But, if you draw a line from, say, here to here, you get kind of just south of east. If you go from the zenith through the nebula, that gets you north of east. So some constellations are very long, like Hydra here. That's the longest and biggest constellation in the sky. It's only like a quarter of it here is visible. So some constellations, of course, are pretty big. So what I'm going to do is I'm going to draw a line from the zenith through the bright star Regulus. Sometimes you can just go right through the center, but let's make it a little harder and go through Regulus. And you can see we get to a point nearly due east. So we've already eliminated, south, west, and north, but we want to look maybe just a little bit south of east. So not exactly east, but pretty close to it. So that's your first step. Ask yourself, what direction do I look in? Go from the zenith through Regulus, and you get your answer, in this case, nearly due east, but a tad south. Now draw back up your line. And you can see Regulus is pretty close to the horizon and far away from the zenith. So you don't want to look really high. You kind of want to look low, but, not too low. Maybe about a quarter of the way above the horizon. So face east Look just a quarter of the way above the horizon, and you should see a bright star with this backward question mark pattern here. More on that later. And then you can go off a little bit toward the north, but toward the horizon, and you'll see this little right-angled triangle there, and that's where Leo is. So there you go. That's how you can find any star or constellation in the sky. And learning to do this is invaluable. It's an invaluable skill to learn before you move on to binoculars and a telescope. Now, of course, I mentioned those pesky smartphones will ruin your night vision. So you might wonder, well, what can I do to see my star map at night? Now, you might break out that white light on your phone again, but again, put the phone away. At night, it's worthless. Get yourself a good old-fashioned red-lighted flashlight, a flashlight that gives red light. And that's what you can see many amateur astronomers doing at some very nice star party on a very clear night. So yep, red lights at night keep stars in sight. And of course, you can make your red flashlight at first. You can use red cellophane, red plastic from like a shopping bag, red tape, like maybe from a tailgate repair kit. But eventually, you'll want to buy your own dedicated red lighted flashlight. And of course, they all basically have LEDs today, which is really great because, when you use a red flashlight, you want to keep it dim. Some people have the perception that no matter how bright it is, if it's red, it's fine. And that is not true. You want the light to just be bright enough to just be able to read your star chart, okay? So, and you might see some stuff online that green works, but a while back, Sky and Telescope did a study, or at least they had someone do a study, and they discovered there's this amber color, not quite amber, but close to that, that's actually better than red. But, red is so prevalent that it's going to be hard to get rid of red flashlights out there. So what happens here, of course, is if you use a bright red light or white light, you ruin your night vision. And you really do have night vision. For most people, they think it revolves around the iris. Your eyes get your pupil. Your pupil gets wider, when it gets darker. But there's more to it than just your pupils being dilated. The eyes produce this light-sensitive protein called rhodopsin. And so your iris, the proper part I'm talking about here, has two parts. There's the cones and the rods. Now, the cones in your eye are color sensitive, and they're what you use to see color during the day. But at night, when your pupils are dilated and you start building the rhodopsin, the rods take over. Now, the rods are not very color sensitive, but they're light sensitive, so they're really good at seeing at night. And what happens is, yes, your pupils dilate, that they get wider, but over 20, 30 minutes for young people, the rhodopsin builds up in your eye and makes it even more dark adapted. For older folks, like me, I guess now, it takes up to 40 to 50 minutes to become dark adapted. And what happens is when, somebody flashes you with a white light or a car light, the rhodopsin is bleached and you have to start the dark adaptation process all over again. So if you ever go to a observing session or a star party and you got a white flashlight, people, usually they're polite, but except maybe like the Texas Star Party, I've heard many people get yelled at, turn off that white light, because they get very upset, when they're at a very dark site like what they have at the Texas Star Party. So be sure if you go to a group gathering, you bring a red light, but for your own night vision, get yourself a red flashlight. Now, of course, there are some lights you can't avoid. Hardly any of us can. And this gets us into a little side topic here called light pollution that I want to talk about. This is a very important topic for amateur astronomers, so we should spend a little bit of time on this. So, of course, light pollution, as we well know, is man-made or human-made light sources that shine up into the sky where they're not needed by anybody. I mean, sure, they do make cool pictures from the International Space Station. Of course, you can see some aurora here, but you can clearly see the outline of Michigan, at night because of all the poorly lit cities. Here's where I live. There's Kalamazoo right there. So I'm kind of just on the north end of that, right about there. So I I'm waving if you can't see me. So of course, light pollution has its problems. There's lots of problems with light pollution. First and foremost, for we amateur astronomers and professional astronomers, is it impedes astronomy researchers and hobbyists like us. It ruins the night sky, our birthright. But there are many more important issues like safety issues. Bright lights can temporarily blind us and cause accidents. And there are many health concerns. They disrupt our circadian rhythms. And now, in the house that I grew up in, we had this obnoxious neighbor that had a security light pointed right at my bedroom window. It was supposed to be on a motion sensor, but it never worked right. So, pretty much all year long, I had to put up with this bright light shining right in my window, except during the summer because they went to a cottage. And the moment they pulled out the driveway to go to their summer cottage, I went next door and with the ladder and I unscrewed the light bulb just a little bit every summer, just so I could get some sleep at least during the summer. But yes, this can disrupt our sleep patterns, and that can affect your performance, in school and work, and maybe make it dangerous for you to drive if you're a little sleepy. And of course, you're at a higher risk of developing prostate and breast cancer because at night, when you're usually sleeping, your body produces melatonin. And again, it's only produced in darkness, and this has been shown to help prevent reduced tumors. So if you do have to work overnight, or you just have bright light shining in your windows, you are at a higher risk of developing prostate and breast cancer. That's why the American Medical Association has declared light pollution a carcinogen. And there are economic impacts. We waste over $110 billion per year of energy worldwide. And it's energy wasted, on lights that go up into the sky where nobody needs them. Nobody wants them there, but they do it anyway because the people that design these fixtures are uninformed. And the people that buy them are uninformed. And there are those ecological impacts. They can affect plant growth. They affect migrating birds. They can fly around buildings until they get exhausted, or they crash into buildings. And millions die every year during their migration periods. And of course, there's sea turtles that mistake the glow of electric lights in like a parking lot with the shimmering of the ocean surface, because when they first hatch, by instinct, they go to the brightest source. And if that's a parking lot, they'll either die from dehydration or get eaten by predators or get ran over by cars. I've seen websites with pictures of that, but I'm not going to show it to you because that's just terrible. Poor little sea turtles. And of course, there are environmental impacts too. Because of this excess energy we waste, that adds 21 million tons of CO2 into the atmosphere every year. And so light pollution is a source of climate change. If you're a climate change denier, well, sorry, you are wrong. You are so wrong. Okay, so here is downtown Kalamazoo. And of course, if you live in Kalamazoo, you probably know this picture is a little bit dated because there's now a ramp or like a bridge going from this building to the parking structure that you can't really see here. But I used to teach in this building right here. So after one class, I took this picture because right outside a educational institution is like the stupidest lights in downtown Kalamazoo. Because, what are these lights supposed to do? They are supposed to shine on the ground so we can see where we are going. But look at this building across the street where there's a ramp now, it's totally lit up when the light should be directed to the ground. So lighting should be done so it has full cutoff fixtures and it goes to the ground where we need it. Nobody is saying get rid of these lights, but just design them properly so they do what they're supposed to do, and only have them on, when you need them. There's no reason for, car lots to be lit up bright enough to do brain surgery. Today, we have security cameras that are really, really bright and sharp in the infrared that give off infrared light that nobody can see. So there are many preventions and solutions. Of course, replace wasteful lighting with fully shielded fixtures. So, again, you want the light to go where it's needed, not in any other direction, not up into the sky, not out in all directions. And, use LEDs because LEDs are taken over with a color temperature of 3000 Kelvin or less. Many cars and many streetlights now have the high temperature, 5000 Kelvin, that are just bright and blue and awful. And of course, only illuminate places that need it when it needs it. So turn off unnecessary lighting. So now let's take a tour of the constellations by season. And by season, I mean these are the constellations that are visible in the evening at every spring, for example. So the spring is a great time to learn the night sky because the Big Dipper is high overhead in the spring, and the Big Dipper can be used for a lot more than just locating Polaris in the sky. So you'll notice we have the pointer stars here again, but this time let's focus on the handle. So the handle of the Big Dipper has a bend or an arc. And if we follow the arc, it leads us to Arcturus. So Arcturus is the brightest star in the constellation Boötes, the herdsman. And yeah, from the way they draw the stick figure, and this is a pretty universal way of drawing the stick figure, it just doesn't look like a herdsman at all. So there are two very popular asterisms for Boötes. Now, in early spring, like April and May, I like to refer to Boötes as the kite. And yes, it does look like a big diamond-shaped kite in the sky, like this. So Arcturus is where you attach the tail. And you can imagine some stars, being the tail if you want. But even though Boötes is kind of a spring constellation, you can see it well into summer. So when we kind of transition from spring, kite flying season into summer when it's nice and hot, I like to imagine Boötes as an ice cream cone. So the bottom of the constellation, where Arcturus is, that's kind of the tip of the cone. And there's one scoop of ice cream in the cone. So it looks like that. Yummy. And then you can see nearby, there's this C or U-shaped constellation called Corona Borealis. Now, I know we're very sensitive about this word now. In fact, right after the pandemic, I gave a talk on the constellations to some Girl Scouts. And when I mentioned Corona and Corona Borealis, they booed me because nobody likes to hear this word anymore. But, we in astronomy have been using this word for a long time, and we're taking it back. It's ours. So Corona Borealis, of course, means the northern crown. But it's also an asterism. It's the other scoop of ice cream that just fell off. So darn it, I hate it when that happens. So we can continue onward here. We can follow the arc to Arcturus and then drive a spike to Spica. Now, some people say follow the arc to Arcturus and speed on to Spica, but to me that never made sense. You arc to Arcturus, so you should spike to Spica. And Spica is the brightest star in the constellation Virgo. You can see, she even holds up her arms in a V-shaped pattern to remind you of her name, but she's really gathering the warmth of the sun. And you can see she has like a leg here and a leg there. So there's Virgo, another prominent constellation of springtime. Now we can go back to the Big Dipper again. Previously we used the pointer stars to go off in this direction toward Polaris, which is off the screen. But now we can go the other way. Follow the pointer stars in the opposite direction, and it takes you right to Leo the Lion. So you can see we didn't need to use the star map at all to find Leo. Just use a simple star hopping technique, and it takes you right to it. So yes, following the arc to Arcturus, driving a spike to Spica, and using the pointer stars to find Polaris, or the pointer stars to find Leo, this is star hopping. In this case, moving from, say, star to star, or from star to constellation, or so on. And star hopping is an invaluable skill to learn when you progress to binoculars and then a telescope. So here we have Leo the Lion. Regulus is his heart, and the head and mane of the lion is another asterism called the sickle, named after an ancient farming implement. But it's the mane and head and heart of Leo the Lion, while the nebula is the tail of the lion. And note the name, the nebula. We'll come back to another version of this name later. So this is Leo's hindquarters here. So here he is up in the spring sky. Now, of course, he's a lion, so he could be roaring, but he's most likely yawning because he's a lion. You know, he's a big cat. They sleep a lot. Now we get into the summertime when most people venture out under the stars. You know, maybe you can venture out in the spring and the winter, but for us in Michigan, that gets pretty hard. Not only is it really cloudy, but it gets really, really cold. So in the summertime, it's also very easy to learn the night sky because we have this dominant asterism overhead called the summer triangle. And it's called the summer triangle because it rises in the east at the start of summer. So here we have Vega in the constellation Lyra the Lyre, which is like a harp. Then we go to Deneb. So remember, the nebula was the tail of the lion. So Deneb is the tail of the swan, Cygnus the swan, to be precise. Now, the stars of Cygnus, at least the bright stars, like the three stars here and these three stars here, maybe kind of four, are another asterism called the Northern Cross. But we go out a bit further to draw like the wingtips. And then the last star in the triangle is Altair. Now, I like to draw it with a triangular body like this, but Starry Night, the program I use to generate these pictures, doesn't show it that way. So it has a triangular body. There's one wing going here and a wing here, and tail feathers right out there. So there we are. We have the lyre, or kind of a harp, the swan, and Aquila the eagle. And for some reason, the eagle is making off with someone's young kid, but I believe that story has been lost in mythology. Now, in the summer, you can look low to the south, at least at mid-latitudes for us in Kalamazoo. And you can see two other prominent constellations of summertime, Scorpius the Scorpion and Sagittarius the Archer, which is actually a centaur, you know, half man, half horse. So Antares is the heart of the scorpion. And kind of like Cygnus the Swan in the previous slide, Scorpius does look like what it's supposed to. You know, Boades doesn't look like a herdsman at all, but Cygnus does look like a swan, and Scorpius does look like a scorpion. We kind of have three stars in a row here, kind of reminiscent of Orion's belt, but this is his head. Again, Antares is the heart, and we follow the scorpion's tail to the stinger stars right there. And then nearby, we have Sagittarius the Archer, but everyone identifies Sagittarius by an asterism called the teapot. So I could sing the song, but of course I'm like tone deaf, so I won't do that. But we have the handle. We have the top of the teapot where the tea goes in, and we have a spout. Of course, there's the container where the tea gets boiled, right? And then we have a teaspoon nearby because, of course, we prefer our tea with sugar. At least some people do. So here's what they really look like. So yeah, Scorpius does look like a scorpion, but of course, Sagittarius definitely looks more like a teapot than a half man, half horse. And here they are on a different star chart. Here we see Scorpius again and the teapot. But rising from the spout of the teapot is steam. And if we follow that steam, which is the light from many stars in the disk of our home galaxy, the Milky Way, we go through the summer triangle all the way to this W or M-shaped constellation called Cassiopeia, the Queen, which is many people's favorite constellation. So of course we see the familiar W, but at certain times of the year it does look like a letter M. And the W is supposed to be her throne, but many figures show it as Cassiopeia herself. But again, the W was supposed to be the throne that she's sitting on because she's the ancient queen of Ethiopia. Now we go to autumn stargazing, which is still a pretty familiar sight to many amateur astronomers. You know, the weather in October, at least in Michigan, can be pretty good. So we get to see a lot of these star patterns. And we come back to Andromeda and Pegasus that we met earlier. So, of course, only these three stars in the Great Square are part of Pegasus. This is actually the back of the winged horse. So he is upside down in the sky, at least from the northern hemisphere. This is his front. This is the top of his head here. Enif is kind of his nose, I guess you could say. Maybe an eye, but really his nose. And there's like a pair of front legs here. Now, maybe these used to be his back legs, but now these groups of stars belong to Andromeda. And Alpheratz, as we saw earlier from the constellation boundaries, is the head of Andromeda, the princess. And of course, we see Andromeda chained up because she's, chained to the rocks in the harbor. And so Andromeda, Pegasus, Perseus, Cetus, Cepheus, Cassiopeia, all those constellations that are prominent in the fall are part of another massive story, but I'm not going to bother to tell it to you today. So for reference, I will tell you to watch the early 80s movie Clash of the Titans. Yes, I know there's a remake, but it's awful. Watch the original Clash of the Titans, and it tells this ancient story with Andromeda and Perseus and Pegasus and all that. Now we get into the winter sky. And for many of us, this is the sky we see the least because in Michigan, it's almost perpetually cloudy. And if it is clear on a winter night, it is very cold. But the winter sky has a lot to offer. Of like the 25 brightest stars, 12 are visible in the winter sky. So it has lots of bright stars. And so in the spring, we have the sickle. In the summer, we have the summer triangle asterism. In the fall, we have the great square. But in the winter, with all those bright stars, we have the winter hexagon. And it's made up of many stars, including Rigel and Orion the Hunter, Aldebaran and Taurus the Bull, Capella and Auriga the Charioteer. You can just really draw it to Pollux and Gemini, but we can throw in Castor and Gemini. We got Procyon and Canis Minor, and again Sirius, the brightest star in the night sky in Canis Major, with Betelgeuse inside. Now, there's also the winter triangle with Betelgeuse, Sirius, and Procyon, but we already have a summer triangle. We don't need a winter triangle. We got a winter hexagon, and it's much, much better. So yes, the sky is this menagerie of ancient figures and animals and devices and stuff like that. It's pretty crowded up there when you get right down to it. Okay, so everything we measure in the sky, the angular diameter of objects, the angular separation of objects, is all done with angles. So, for example, we see this woman who's, trying to measure the angular separation of a young waxing crescent moon and perhaps a bright star. Maybe it's a planet. So, yep, we don't hold up a ruler and say, well, it looks like the moon and Jupiter are 5 inches apart. We measure their separations in angles. And of course, this includes directions as well. So, to use directions, we use azimuth and altitude at night. Now, this is a really easy system to learn. So azimuth is the direction in degrees. So due north is 90 degrees. And remember, east and west are backwards. So as we turn 90 degrees, we face due east, which is 90 degrees azimuth. Add another 90, and due south is 180. Due west is 270. So you can chop that up even more. You can say, northeast, which is halfway between north and east. So divide this by 2. That's 45 degrees. And just keep adding 45. So southeast is 135. Southwest is 225 degrees. And northwest is 315 degrees. And you can keep dividing that by half, so northeast is 22.5 degrees, but I won't bother to fill in the rest from there. I'll let you do that. So azimuth is the direction in degrees. Now altitude is the height above the horizon. So the horizon itself is 0 degrees. And for us in Michigan, the first 5 degrees or so is usually trees. For some people, it's even more. But halfway up is 45 degrees, all along like a circle here. And the zenith, the point directly over your head, is 90 degrees. So, yep, azimuth goes full circle from 0 to 360, 0, 360, same thing. But altitude only goes from 0 to 90. Now, how do you measure these angles in the sky? And you might ask, why is this important in the first place? Well, if you're going to use websites I'll talk about later to find out where the space station is going to appear, it's going to tell you where to first look for it in terms of azimuth and altitude. And if you want to know what direction to look for a rising constellation, it'll tell you by azimuth or altitude. So you might be thinking, do I have to buy a sextant now? Holy cow. Nope, you don't need a sextant. You can just use your hands. So these are with your hands at arm's length. And, so your pinky finger is about 1 degree. So you should be able to easily cover up either the sun or the moon with just your pinky alone, because they are less than 1 degree in angular diameter. But what most people do is they just use their closed fist and, stack it. So what you can do if you want to measure altitude is, hold out your fist where the bottom of your fist is lined up with the horizon. And then the top of your fist is 10 degrees. And then you can stack your fists. And what you can do is what I call the Polaris check, because the altitude or height of Polaris above your horizon is based on your latitude, or really vice versa. So again, I live at a latitude of 42 degrees. So if I hold my fist, so the bottom lines up with due north, and the top of my fist is 10 degrees, I stack my fists, 10, 20, 30, and I should get 40 degrees for Polaris. So there are ways you can check yourself. And you'll notice that, yes, we have this breakdown here. So it's very familiar, even though it may not look like it at first. But think about it like this. 1 degree, which is your pinky at arm's length, is equal to 60 arc minutes, which is equal to 3,600 arc seconds. Now, again, this looks familiar because you can say 1 hour equals 60 seconds, or 1 hour is equal to 60 minutes, which is equal to 3,600 seconds. So same thing. And we can do some math here. Half a degree, which is the angular diameter of the sun and moon, on average anyway, is about 30 arc minutes. So 1 arc minute is equal to 60 arc seconds. And 1 arc second is equal to 1/3600th of a degree. It's not terribly important to know that, but hey, I'm a math guy. I can't help myself. So besides the Polaris check, another way you can check your altitude measuring system, or even your azimuth measuring system, is to use the Big Dipper scale. So the Big Dipper itself is about 25 degrees long. So again, your thumb and pinky finger at arm's length, if you hold out your thumb and pinky finger, that's about 25 degrees long, which is the length of the Big Dipper in the sky. When you do hold out your thumb and pinky, you might think, boy, the Big Dipper sure does seem bigger than that in the sky, but that's just an illusion. So your fist should be able to fit, right into the bottom of the bowl, for most people, unless you have like a really big hand. All right, so to finish up here today, let's talk about everything you can see in the sky with just your eyes alone. Because again, people are always so anxious to jump right to the telescope. So, when you're getting started, there's plenty to see with just your eyes alone. So let's talk about some of them. One of them are planetary conjunctions. Sometimes the planets gather together in the sky. Now, there was the great conjunction of Jupiter and Saturn back in 2020. That was actually good with a telescope because Jupiter and Saturn were so close with a telescope, you could view them through really long focal length telescopes. Like we got together in the club to look at Jupiter and Saturn through our 16-inch telescope, which is really long focal length. But most planetary conjunctions are, best with just your eyes alone. Like this one here by a guy that took this image in Poland in May of 2013. Venus, Mercury, and Jupiter were so far apart, you couldn't even use binoculars. But to the naked eye, this was a great sight. And of course, planets gather together like this all the time. You just have to keep track of it. And sometimes you might get a close conjunction of Venus and the young crescent moon. Now, this you could observe with binoculars. We'll talk about that again next time. But, this is a very nice sight with the unaided eye. You get to see the moon and Venus, and you get to see Earth shine. You get to see the old moon in the new moon's arms. So that's a very enjoyable sight to the naked eye. Now, you might ask, now, how do I know if I'm seeing a planet or a star in the sky? There are kind of ways to figure that out, even if you don't have like a star chart. You walk outside, you see a bright star, maybe high in the south or high in the west, and you might wonder, is that really a planet or is it a star? Well, there are ways you can figure that out, again, with no star chart. So number one, of course, if you do have binoculars or a telescope, is planets, especially, the inner ones, maybe not so much Uranus and Neptune with small telescopes, they resolve into disks when viewed through binoculars or a telescope. When Mars is close, it looks like a disk with binoculars. And of course, planets are generally brighter than stars. So if you see a planet, or star high in the west, that's brighter than anything else in the sky, it's probably Venus as the evening star, because Venus is so bright, it can cast shadows. And Jupiter is also brighter, I think most of the time, than Sirius. Maybe sometimes it's not so much, but usually it is. And you'll notice that the stars twinkle because the stars are so far away, they really are just point sources. Again, they do look like they have sizes. Even when you view stars through a telescope, it does look like they have a disk, but they really don't. That's called an airy disk. More on that in part 4. But, stars are so far away that their light gets bent and distorted by the atmosphere. So we call that bad seeing, or the more technical term is scintillation. So planets are actually little disks in the sky. So they're not nearly as susceptible to seeing conditions as stars are. If, Jupiter or Venus gets very low and the scene is really turbulent, they can flicker a little, but by and large, the planets really don't twinkle. And of course, planets lie along the ecliptic. So if you can see, where the sun set and maybe the moon's up in the south, you can draw a curved line from the sun through the moon to like the eastern horizon, and that basically traces out roughly the path of the ecliptic. So the ecliptic is the apparent path of the sun in the sky, but because the solar system is pretty flat, the planets are always near the ecliptic. And of course, from one night to the next, the planets move. So if you're drawing a constellation and it has a planet in it, include the planet. Then come back, maybe a week later, draw the constellation again along with the planet, and I bet you'll find that the planet is not in the same position it was a week earlier. So planets move. You can't really tell that, during a single night, but over several nights, you can. Now, of course, one of the most enjoyable things to see with just your eyes alone are meteors. Now, you can see a sporadic meteor that, doesn't really have an origin. It's just some random meteor every 10 minutes or so, if you're looking for one. If you're stargazing long enough, you'll see a meteor or shooting star every 10 minutes or so. So, of course, here's a really bright one. Now, if a meteor is about the same brightness as Venus, about minus fourth magnitude, we call that a fireball. Now, if a fireball explodes in a bright terminal flash at the end of its path, that's known as a bolide. It suddenly explodes. You can see this one did not, because it kept going on here. But if it's like boom, if there's like a single point here, then yeah, it was a bolide. But this is what I would call a fireball here. And then if a meteor leaves a vapor trail that usually fades in a few seconds or can last for several minutes, that's called a persistent train. So you're really lucky if you get to see one of those. They're not rare, but I don't see them, of course, every day. Now, of course, we do, again, have sporadic meteors, but some meteors do have a common origin, and we see them at the same time every year, and these are called meteor showers. So here's a photographic composite. Of course, this isn't one photo. It's many images put together. And you can see that at first glance, it does look like these meteors are moving in different directions. We got some going down. We got some kind of going up toward the north and, all kinds of different directions. But trace back their path, and they seem to come from a point right around here. So this point in a meteor shower is called the radiant. So, this, for example, is the Perseid meteor shower that we see every August 11th or so, August 11th or August 12th. And these come from a different source. But before we move on, I'll mention that, again, I live in Michigan. It gets pretty cloudy here. So we often get clouded out for many of the cooler meteor showers, like the Geminids or the Quadrantids in January. What you can do is you can listen to meteors on your FM radio dial. So what happens is ionized trails of meteors reflect transmitted signals from FM radio stations hundreds of miles away, from FM radio stations that you can't pick up because they're too far away. So what you can do if it's cloudy, or even if it's clear, is you can tune your FM frequency to one of these distant radio stations that, maybe several hundred miles away. So, of course, they usually just sound like little blips, like, it just sounds like a really brief little burst, but sometimes they can have really cool noises. And there's one clip here I have been playing for people for many, many years. So here's one of my favorite meteors that left a cool radio noise. Here we go here. Oh, I always forget. I got to turn the laser pointer off. One more time, because it's so cool. So yeah, it sounds like a humpback whale, but that is a meteor burning up in the atmosphere. So again, you have to be at an empty FM dial. So what about these meteor showers? So most meteor showers, with the exception of one or two, they come from comets that come close to the sun. So I always like to call comets the pig pens of the solar system. You guys know Pigpen, right? From the Peanuts. Here he is here. He's the one that never likes to take a bath. He's always dusty, and he leaves like a little trail behind him. Or if you want to do another analogy, say you're in the country and you have to cross this dirt road, but you're waiting for this truck to go by. And of course, as this old pickup truck drives by, it kicks up this cloud of, dust. So comets kind of do the same thing, but as they orbit the sun, they leave little bits and pieces of themselves behind as they slowly decay. And so if one of these comets comes near or crosses the Earth's orbit, and Earth passes through this point, at the same time every year, we collide with these particles and we have what's called a meteor shower. And again, they definitely have a common origin. You can trace back their path to the constellation they appear to radiate from. Now you'll notice in this drawing here, this kind of comet stream has a dense clump in it. And that's the case for the comet Tempel-Tuttle, which orbits the sun every 33 years. So comet Tempel-Tuttle is the source of the Leonid meteor shower that occurs every November. But every 33 years, we intersect this dense clump and we have what's called a meteor storm, where you can see not maybe the typical 15 meteors per hour, like what we have with the Leonids, on a normal year, but maybe thousands, tens of thousands, or in the famous case of the meteor storm in 1833, hundreds of thousands of meteors per hour. And this may happen again in the year 2035. I didn't get to see it in 1999, 2000, 2001, because again, Michigan, it was always cloudy. But here's a list of the annual meteor showers. Of course, I mentioned the Quadrantids. That comes from an extinct constellation that's now part of modern day Draco. If I've ever seen a Quadrantid, I don't remember it because, again, in early January, we don't see the sky very often. But the two most famous ones here are the Perseids, which is probably the most famous because it occurs in summer during one of the clearest months in the year, at least for us in Michigan. And there's also the Geminids. This past Geminid, we had clear skies, but it wasn't a great producer this time around. But during 1 year with the Geminids in 1998, I counted roughly 125 per hour, which was remarkable. So meteor showers are great because you never know when they're coming. And when you see one, it always makes you, light up and you're like, wow. And then it's gone in a flash. Now, of course, today, starting in the 1950s, we see plenty of artificial, human-made objects pass overhead, and these are called satellites. In the image here, we see one that appears to have burn up, but no, it didn't. This was a iridium flare, which were from iridium communication satellites that had highly polished surfaces. But now the original iridium satellites have been decommissioned and we no longer see iridium flares. They could still technically happen, but because the satellites are decommissioned and no longer being oriented properly, they're no longer possible to predict when they occur. So if you do see something suddenly brighten and fade back down, it could have been a defunct iridium satellite. But typically, satellites travel from north to south. They have a steady brightness. And of course, they make no noise, or they don't flash or anything. The most prominent one you can see is the International Space Station. It can reach a magnitude of -6. That's brighter than even Venus. So, of course, the International Space Station, we'll put up a picture there of what it looks like today, is the largest human-built object ever to be placed in orbit. Of course, it was done so in pieces starting in November 1998. It has an overall length of 109 meters, overall width of 73 meters, and it orbits the Earth at a speed of 17,100 miles per hour, or 27,600 kilometers per hour. And so it completes one orbit about the Earth every 93 minutes. And you can use websites like Heavens Above to predict when the International Space Station will pass overhead. Yes, there are apps you can get for your phone. There's one called Spot the Station, and it can tell you when the International Space Station will be visible. But I always prefer to use heavensabove.com. It's heavens-above.com. Now, sometimes you might see this. I decided to keep the audio in here so you know it's a real video. You can see some bats fly around, which are not my favorite, but I've seen two of these. So what we're seeing here are Starlink satellites from SpaceX. So the first batch uh, of these satellites, which are used for global internet and cell phone use, was placed into orbit in May of 2019. And so they're often released in batches of 50 or 60. I haven't had time to count all these yet. So if anybody wants to count all these and tell me how many there were, it has to be at least 50, maybe 60. But to date, uh, January 2024, there are over 5,300 of these things in orbit. And the number from SpaceX alone may increase to 12,000 or even 42,000 of these things in the years ahead. They do spread out over time, but they are becoming a menace to both amateur and professional astronomers because they are polluting the night sky. I mean, yes, they've been very useful in the war in Ukraine for the Ukrainians, but for us, they are ruining the night sky. So other companies may launch their own constellation of satellites into the sky like this, and we amateur and professional astronomers are going to have to stand up and say, no, no more junk in the sky. Over half the satellites in the sky now are from this junk here. So we just don't need it. There must be a better way to do it than release hundreds of these stupid things in the sky. And again, another spectacular thing you can see with your eyes alone is the aurora. If you're in the northern hemisphere, it's called the aurora borealis. If you're in the southern hemisphere, it's called the aurora australis. So the source of the aurora is ultimately the solar wind. So the Earth has a magnetic field and, of course, an atmosphere that protects us from the solar wind, this constant stream of charged particles from the sun, electrons and positively charged ions. And so the aurora occur about 130 kilometers or 80 miles above the surface when energy in the solar wind is guided by Earth's magnetic field and excites gases in the upper atmosphere. So two ways to excite gas is through collision or absorbing photons. In this case, they collide with particles from the sun that causes the atmosphere to glow at the north and south poles, normally. So if you've never seen the aurora, here's another cool video. And digital cameras are getting so good, so sensitive, that you can record aurora in real time now. So I like this video here because you see this woman moving, normally. So this is not a time lapse. This is done in real time. And it gives you a sense of what the aurora can do. There can be shafts, curtains, and pretty soon here it'll point overhead and it'll show you what's called the aurora corona. Here we go. So when it's overhead like this, it looks like a distortion in the space-time continuum. I've seen it like this before, from my home here in Kalamazoo, and it is one of the neat things to see. It looks like the Enterprise should pop out of this thing, traveling back in time at any moment here. So the green and red colors are from atomic hydrogen, while blues and deep reds are from excited nitrogen gas. But again, it's remarkable. Another great thing to see with your eyes alone are great comets. They don't come along very often, so when one does, you got to kind of just drop everything and go out and see it. And that's what I did when I saw my first bright comet in 1996. I was too young to see Comet West in 1976. I was only like 5 years old, probably not even 5 yet. But so Comet Hyakutake in 1996 was my first bright comet. And then there was Hale-Bopp in 1997. Then the Southern Hemisphere got their turn in 2007 with Comet McNaught, which was the brightest comet in the past like 30, 40 years. And then in 2011, there was Comet Lovejoy. Of course, they all have various designations, but from the past 30 years, those are the four great comets we've had. The one shown in the picture here is Comet Neowise. And yeah, Comet Neowise put on a really respectable show in the summer of 2020, but from, urban sites, it was not really visible to the naked eye like Hyakutake, Hale-Bopp, McNaught, and Lovejoy were. It was a great binocular target and a great photographic target, but Neowise was not a great comet. So finally, the thing to see in the sky are eclipses. We have lunar eclipses that occur when the moon is full, and we have solar eclipses that occur when the moon is new. But of course, we have a full moon or a new moon every 30 days. But we don't have a lunar or a solar eclipse every 30 days. Why not? And the reason is simple. With respect to the Earth's orbit, called the ecliptic, the moon's orbit is tilted by 5 degrees. And it wobbles too. The moon's orbit isn't steady. It wobbles or precesses. So sometimes the moon's shadow is too high. And sometimes the moon's shadow is too low for a solar eclipse. And vice versa for a lunar eclipse. Sometimes the moon is above Earth's shadow, and sometimes the moon is below Earth's shadow. So we don't get lunar or solar eclipses every month. They occur on average every 18 months or so, but lately we've been getting them every 6 months. There was a hybrid solar eclipse, that went from annular to solar to annular in April of 2023. We had an annular eclipse in October of 2023, and we'll have a total solar eclipse in April 2024 and an annular eclipse in October 2024. So right now, we're getting one every 6 months, at least some form of a solar eclipse, not necessarily total. So here we have a lunar eclipse. So in this case, as with all eclipses, we have a 3-body alignment called the sun, with the sun, earth, and moon in a straight line, which we call a syzygy. So in this case, we have the sunlight coming out, it hits the earth casts a shadow, the Earth's shadow is about twice the diameter of the full moon, so we get a lunar eclipse. So if you're in the penumbra, you see a partial eclipse. Just part of the moon gets kind of dark, but doesn't really ever do anything. It doesn't really change color or anything. And then if you're in the umbra, then there's no direct sunlight visible. But again, in the penumbra, there's some sunlight that still shines on the moon. You get a little bit of the Earth's shadow, but not too much. But if you're in the umbra, there's no direct sunlight being cast on the moon. So you might wonder, well, if there's no way for sunlight to reflect off the moon to our eyes, how come the moon just doesn't disappear altogether? And the answer is the Earth's atmosphere, which acts like a prism. It bends the light, but only red and kind of orange light is long enough wavelength to make it through the atmosphere. And of course, our atmosphere scatters blue light, making the daytime sky here blue. So you can kind of say that when the moon turns kind of red, it's from all the sunrises and sunsets around the world at that time. Now, if you've never seen a lunar eclipse, here's a cool time-lapse video that I found that I'll share with you. And I give credit here to the source. Here's the curved Earth shadow. You can see the umbra creeping across the surface. And as it gets deep in the umbra, that's when it turns that kind of coppery red color, or yes, as the media calls it, a blood moon. But that's a media term. We amateur astronomers don't like to call it that. And there goes the Earth's shadow. And yes, the shadow is curved, proving the Earth is round and not flat like some people's heads that think the Earth is flat. So a lot of people think lunar eclipses occur more often than solar eclipses because they're visible over much larger areas. As we'll see, solar eclipses are only visible along a narrow line across a tiny portion of our planet. But anybody in this region in January 2020, 2019, got to see a lunar eclipse, including me. So I got to see it that year. And of course, if you're in the daytime side, the moon's below the horizon, so you don't see anything. But hundreds of millions of people got to see the lunar eclipse. You didn't have to travel really to see it. Now, the Earth's orbit around the sun is nearly circular, but the moon or the sun is a little bit bigger in January than it is in July, because we are closest to the sun in January as opposed to July. But the moon's orbit about Earth is much more elliptical. So the moon size can change dramatically from, say, one full moon to the next, as shown here. But it's the same thing for a new moon. Sometimes you get a tiny new moon, but if all the conditions work out for a total solar eclipse, but the moon's too far away, it's near or past apogee, you get what's called an annular eclipse. So let's explain this here. So again, the sunlight comes out, it hits the moon, but the moon's much smaller, so its shadow is very small. But guess what? The moon is too far away for its umbra to reach the surface of the Earth. So a total solar eclipse is not possible. And of course, if you're in the penumbra, you just see a partial solar eclipse. But there's another part not labeled here yet. There we go, called the antumbra. If you're in the antumbra, you will see what's called an annular eclipse. So annular means ring, because during annularity, as opposed to totality, you see a ring or annulus of sunlight. So there's the new moon sort of inside the sun. And these are a lot of fun to observe. They are nowhere near as spectacular as a total solar eclipse, but just recently I traveled to Roswell, New Mexico to view the annular eclipse that occurred on October 14th, 2023, because the last one I saw was in May of 1994, and the next in the US is not visible for another 30 years. So I wanted to see this one, and sure enough, I did. And I took lots of pictures. But finally, there's the granddaddy of them all, a total solar eclipse. And if you live in the US and missed the one in 2017, make every effort to see the one coming up here that we'll talk about. So same thing here. The sunlight comes out, but now the moon is close enough to the Earth and big enough, hence big enough, so the umbra, labeled here, makes it to the surface. So the umbra sweeps out a narrow path of totality like this, which is what will happen on April 8th, 2024 in North America. So it begins in Mexico, crosses through the Midwest here in the US, and off to Canada, where they haven't really a prayer of seeing it, because in this region in April, it's pretty much always cloudy. It often is here too, but we have a little better chance of seeing it from around here than they do over here. So if you live in the Northeast or Canada, you're going to want to travel to the US. I'm going down to near San Antonio, right about there. So you want to be in the path of totality and as close to the center line as possible, so you can enjoy the longest eclipse you can. If you're near the center line here in San Antonio, near San Antonio, you get nearly 4.5 minutes of totality. That's twice as long as what we got in 2017. And only along the path of totality can you see stuff like Bailey's beads. And one of my pictures from 2017 here. So these are named after Francis Bailey, who correctly described it, or at least described it so well. Many knew what the cause was, but he was the first to really explain it well. So, the moon is not flat, but rugged. So right before totality, this is seconds before totality, sunlight can peek through, valleys and craters on the moon. So you get this bead here. And you can see prominences as well, but those are best viewed during totality with binoculars. And then the beads here disappear one by one. And so the last of the Bailey's beads, or it could be beads, more than one, depending on what part of the moon it works on, is called the diamond ring effect. And so this is, again, right, just fractions of a second before totality. But the thing to see during totality is the corona itself. Now, this is far better than you can see with your eyes alone, but if you've never seen the solar corona, it's the most amazing thing you can see with just your eyes alone. You need no special protection. But for, of course, most of the eclipse, you do. For Bailey's beads and the diamond ring effect, that's when you can take your maybe special glasses off or not look at a projection. But pretty much all the partial phases, you got to take special precautions to avoid damaging your eyes. So I don't want to spend too much time on this because you'll probably hear this a lot in the months ahead since we are approaching the April eclipse here. And I know what method most of you will probably use, but there are, various safety methods you can take. There are two methods called the indirect method. There's the pinhole viewer, where you make one of these boxes with a little pinhole that projects the image of the sun. So, you're never looking at the sun, but a projection of it. Or you can do solar projection with a telescope or a pair of binoculars. Just make sure no one ever tries to look through the eyepiece, of course, because that would be very dangerous. Now, if you want to do the direct approach, you can use a welder's glass. So if you have, if you weld or know someone that does, you can borrow their welder's goggles or welder's helmet or glass, but it must be number 14 or greater. But what most people do are get themselves a pair of eclipse shades. And of course, the Kalamazoo Astronomical Society, as another fundraiser, is selling eclipse shades in our online store called the Sky Shop. So, there's a lot of things relevant to the Sky Shop in today's lecture. So we do charge $3 a pair, but they do include a nice postcard and an informative, a nice informative postcard along with a little Ziploc bag to keep them in, so they're protected. If you do have a pair left over from 2017 and they don't let any little bits of sunlight through, they are perfectly fine to use. So they never expire. They are good for many, many, many years as long as you take good care of them. So, this is the method most people use because it's cheap and it's really easy. Now, you can get solar filters for binoculars or a telescope. I did that backwards here, but we'll talk about that again in part 3 and part 4. So we will come back to that. So if you do miss the eclipse on April 8th, 2024, and you're like me, you can't afford to travel to destinations far to see the other eclipses over the next 20 years, yep, you got a 20-year wait. The next isn't until August 23rd, 2044. That'll be visible in the Northwest here and Canada. But then we have a really good one the year later on August 12th, 2045, that goes from coast to coast again. And that's over 6 minutes long. So I hope to make it for that one. The one I would love to make it for is September 14th, 2099, because I don't even have to leave home. But I'm not going to be around for that one. So if you can do it, do it. Become an eclipse chaser and travel the globe and stand in the shadow of the moon. It's one of the most amazing things you will ever see. So there you go. Those are all the things you can see in the sky with just your eyes alone.